Welcome to CSE 31, Lecture 16, Part 1. Hope everyone is doing well at home and stay healthy. So before the lecture, let us go into the announcement. Okay, so Project 1 is due already. And starting from next week during lab, I will allow you to do the demo to your TA. So next week, you will just do the demo as well as your demo of Lab 8 as well, because next week we won't have new lab assignment. Instead, I will give you the Project 2. So I'll show more, I'll talk more about the Project 2 later when I announce the assignment. Okay, so just remember, next week, the week of April 13, we're going to start doing the demo of your Project 1 during lab time. And this week we have Lab 8, and Lab 8 is another exercise on working with functions in assembly language, and especially with recursive function, a function calling another function. And when we do that, make sure that you have to manage your stack memory well, because every time you call a function, you are extending or pushing another stack into the memory. Okay, so which means that when you implement the recursive function, you are actually keep pushing the same stack frame into the memory. Okay? And homework 5 is due this Friday, so make sure you finish it before the assignment is closed, and then click the submit button. And I have also assigned new homework 6 on CAT courses, so click the link from CAT courses, and then it will direct you to SciBook. And the due date is next Friday, April 17th. And if you have any questions regarding the announcement, let me know, email me. And also I have just posted an announcement about midterm 2. So please log into CAT courses and take a look at the announcement and fill out the Google form so that I know what kind of equipment you have. And based on that, I will design my exam. Okay. So last lecture, we talked about how our program is working. Okay, so from the process of running our program in a computer. So we talk about, we start with a program written in high-level language, C, C++, or Java. And when we do GCC, actually a lot of times we just refer that as compilation, but GCC actually takes more than one step to compile a program. So once we have the C file, the compiler takes in the C file and convert that into an assembly program, which is what we write, right? And of course, if we are using an Intel CPU, then the assembly language is different. Okay, so what we learn in class is MIPS assembly language. It's a MIPS CPU. But with your computer, whether you're using an AMD CPU or an Intel CPU, they are pretty much having the same type of assembly language. Okay, so it will be something dot assembly language. Okay, and that assembly language contains pseudo instructions. Do you remember what pseudo instructions are? Anyone? So pseudo instructions means that you can have instructions that cannot be converted to zeros and ones directly. So they are pseudo, right? So for example, move S1, S2. So this is not a real or true assembly language, but that's okay. The compiler's product is just a regular MIPS assembly language or other CPU's assembly language with pseudo instruction. Okay, and the next is the assembler. The assembler will look into the assembly program, remove all those pseudo instructions into true assembly language. And then it will try to find out all the labels and the branch, where to branch to, right? To convert all those so that the output will be a machine file or machine object file for that particular file only. Okay, so this machine file is not the executable file we have yet. Okay, so for each C file in this example, you will have a corresponding O file, but you cannot run this program yet. Okay, so and now if I have a program with many C files, for example, objects, right? Or not really objects, but we can have a group of programs, right? So one calling another file, right? So what do? So now we go into a linker. So once the assembler produce object files for different source files, now the linker kicks in and combine them into one file. So linker. So the input of a linker is just a group of object files. So it depends on how many source files you have. If I have 3 source files, then you have at least 3 object files, and then plus other library files. Okay, so for example, if you use stdio, then now you will also include the library c.o right, into the linker. So this is all internal, the library. So whatever you include in your C file, the object files, the corresponding object file will be loaded together. And also each object file contains the tables. Remember, we have the relocation table and symbol table. So symbol table talks about what you have in your program or in your particular file, and relocation table is listing what you need to complete certain machine code in your program. Okay, so what you have versus what you need. Okay, so now the linker will go through these tables to find out what each object file needs and what each object file has, and then fill out the information, and then finally link everything together and produce the executable, the one that you actually can execute by typing / your program, a.o in this case. Okay, so you can see that when we do GCC with the -o, the GCC compiler actually does compiling, assembler, as well as linker, 3 jobs at a time. And of course, you can use GCC to do all these 3 jobs separately too by using the appropriate tag flags. Okay. So as I mentioned, the linker combines all the object files into one single executable, and that's why it is called linking. Okay. And why do we think this is a good way to do it? Why do we even need a linker? Why not just have the assembler combine everything? What do you think? All right, I'll give you a hint, right? We allow separate compilation. So let's say if I have a program with 20 files, okay, 20 source files, but among these 20 source files, I only need to keep updating one file. Does it make sense to continue or keep compiling the other 19 files every time I make a change in a particular file? No, it doesn't make sense, right? So that's why with the linker in place, we can always just compile whatever individual file that we change, and we leave the other the same, because other source file will have their own object files untouched because we never change it, right? Only the files that we change, we compile it, and now it will have an updated .o file. And because of this particular new updated .o file, I use a linker command to link everything back together. So linking is a lot faster than recompiling. So it doesn't make sense to recompile all 20 files when we only need to update one file, okay? Because the compilation takes the longest time because it translates from C to O, right? So it's, or C to S, right? Assembly language, and then to O. So it's a long process. Okay, so for example, Windows NT with more than 40 million lines. So how many programs have you written so far since your first program, Hello World? Okay, when you add them up, I doubt it will reach 1 million lines yet. right? So think about you have 40 million lines, and Windows is an object-oriented program. So there are so many files combined together. And with the new Windows 10, I would think it is more than 60 or even 80 million lines, right? So that's why it's not efficient to recompile the whole program every time you change a line or two, right? Just think about how much time it takes to load the whole project into Visual Studio if you want to use Visual Studio to update your window, okay, source file. So it's pretty much impossible. Okay, and the whole idea again, okay, the name link, okay, linker is stem from link editor, so you can actually arrange, okay, how you link the instruction, link the program. Okay, so now let's take a look at the illustration, how it works. Okay, so remember, for each object file, you have these three information, right? You have the text, your actual code in zeros and ones. You have the data, whatever you declare in static, right? And then finally, you have those tables to describe what you have and what you need in each object file. So now let's say I have two object files, A.O, B.O. So the linker will combine them and relocate these information, and that's why it's called relocated, which means that you want to group all the program portions together, group all the data portions together, and relocate them. Means that you put them together, and that's why you relocate it. Even for the data of file one, you are kind of relocating it because you are giving space for the text to come in, right? So everything will be relocated. And maybe even the first one, because you have some overhead, okay, to describe, or the header file to describe your program. So that's why the location of the text one probably will be changed too. And so when I say relocate or location, it means that the address will be different. Okay, so whatever you have here associating with the address will be different. So for each object file, all address starts with 0 address, right? But here, definitely you can only have one 0 address. So how you want to assign the address is based on the relocation of the components of your object file. Okay, so this is called relocation. You are relocating the code, the data, and the information of each object file into your final executable. Okay, so let's recap the step. Step one, you take all the text segments from each object files and put them together. So these are the final programs that you have. Right? And second one, you combine all the data segments. So data segment means that whatever data you are supposed to store in the static memory. So any global variable, such for example, will be here. Okay? And then finally, you resolve all the references, because now you have the text segments completed. You know the address of each instruction, right? So which means that by looking at the symbol table and the relocation tables, you now know when I call JAL, where should be the final address of this target, right? So this is happening during the linker, because the linker combine all the text segment, combine all the data segment together. So now you know where to find your target instruction. You know where to find your data in your static memory. Okay, so this is where you consult the relocation table and symbol table to provide the absolute address for JAL or even J. And also, for example, load immediate to load the address of a variable, okay, or load address. So let's review the type of address, okay? Because here we are talking about the relocation. Okay, so in what situation we need to find out the absolute address, okay, in this stage or in this linker stage. Okay, so for PC relative, BEQ, BNE, we don't need to relocate. Why? Remember how to translate BEQ or BNE? So they are I format, right? So, and we use the 16-bit immediate to talk about where to go to if the statement is true, right? For example, if I say BEQ, if the two arguments are true, are the same, then I will go to that location. But the address described in the immediate field is not really absolute. It is relative. Why? We use the count, right? We start from the next line of this instruction and count how many lines to the target that where we want to branch to, right? So we use the immediate to describe the number of lines that is apart from the next PC, right? So that's why it doesn't matter where we move our code, it won't change that, right? Because the linker won't insert any lines or any instructions in between our current program. So again, if you look at the relocation text 1, text 2, the linker still group text 1 within text 1. It's not inserting any text from object 2 to your object file 1, right? So your grouping within your object file remains the same. So if you have 50 lines in your text 1, it stays the same 50 lines when you combine. Okay, but it's just that the address, overall address, will be different. But that has nothing to do with your branch definition, because your branch definition is just to count how many lines apart from your current branch instruction, right? So, which means that this is resolved during the assembler stage, okay, where it is converted into zeros and ones. But for J or JAL, here is the place where you need to resolve the address, because after the assembler stage, we don't know the actual address yet because we haven't combined the object files together. So only after we combine object files, we know the address of every single instruction now. And now we can tell what the address is for each label, and then we can fill out this information. And same thing with the date, with the external call. For example, we're calling a library, right? Printf. And printf is not part of my code, right? Printf is part of the standard library, and we use JAL to call that. So which means that only until we finish the linking, we know the absolute address of that printf, right? And then we can put that address into our final executable. And finally, all the data reference. Whenever I use LUI, right, I want to load the address for store word, load word, or even load an address of a variable, right? So I have to be able to tell where the address is, right? So this is also, again, has to be resolved after the linking. So you can see that for our program, any instruction that requires a real 32-bit address has to wait until the end of linking, when every single line of a program has its own address. Then we can resolve this address at this stage. Sounds good? All right. So here, which instructions need relocation? Okay, editing, which means that which instructions need to be updated or completed in terms of the translation, okay, during the linker. First one, J format, right? Because before combining, we may not have the real address yet, especially for other object files, because after combine, the address will be different. Okay, so JJAL. Load word, store word, same thing. Any address that we need, okay, we won't have that until we link everything together. Okay, so which means that when we do lower storage, we need the address, right? So this one gives us the address, and or this one gives us the register, right, to store the address, right? So this one we need that. Okay. And finally, branches. For the branches, the address is relative, right? It's just going up or down and by how many instructions. So it doesn't really affect the count of number of lines, right, between the target and this branch instruction. So which means that no matter where we move this instruction, as long as the line sticks together, we have the same result. So we don't have to resolve that here. Okay. So how do we resolve that? So again, when we combine the instructions, okay, in the linker will assume the first line has the address of all zeros, okay, or depends. Usually it's actually 004, 0000. It all depends on the CPU and operating system. But for simplicity sake, we just assume that every program starts with the address 0, okay, and that's why you shouldn't use address 0 in your programming. Okay? And since the linker knows every knows the information of every single object code, so which means that it knows how big each object code is, how many lines of code or program does each object file has, as well as how many lines of data segment, okay, and the order of the text and data, right? So since it knows all this kind of information, so the linker can calculate the final size of the program, right? And also count the number of lines, right? So that it can calculate the address of the destination of the jump label, right? Or the address of the data that we need to reference. So this is all done by the linker. Okay, so to resolve the references, so basically again, you look into the symbol table. This is what you have, right? And then the linker will look into your relocation table. This is what you need, right? So by looking at what you need, the linker will go to the symbol table of other object files and see whether it can find what you need. And once it finds what you need, it calculates the address and then put it into your code and replace the address value with the actual value. Okay. So and if it's not found in your program, then it will search the library object file, right? And then again, because the object files are all combined into one gigantic file, it knows every single address. Okay. So as I mentioned, right, it will try to determine the address, okay, and then complete your machine code. And finally, once every line of machine code is completed, now the executable is done. And now you have the complete executable with the header that lets the operating system know how to proceed with the execution when you load the program or when you run the program. Okay. So this is linker, and the linker that I would just mention in the previous slides are called statically linked approach. So here the word static again. So what does that mean? So static, dynamic, what does that mean again? Static memory allocation, dynamic memory allocation. So static means the action is done during the compile time. It's not during the runtime. Dynamic means during the runtime, right? Just like you allocate memory during the runtime, then you use dynamic memory allocation, right? Using the malloc. So you didn't really create a memory until you run the program. So the static linked approach means that you actually link those object files in the compile time, which means that before the program actually runs, you link everything, to put everything into your executable. So this is called statically linked approach. What it means is that all the files, all the object files, as well as the library is now part of your executable. Okay. So now if the library, for example, you're writing a video game that uses NVIDIA library, okay? And now you use statically linked approach. Now the NVIDIA library will be part of your video game. And now tomorrow, when NVIDIA releases a new update of the library, which means that your program is outdated and your program is still running the library that you used yesterday or today. Okay, so that's the problem with statically linked approach. Okay, so if you have an updated library, the update is not reflected inside your executable because if your program has encapsulated all the necessary instructions needed. Okay, so keep that in mind. And that's the drawback. So the alternative way to do it is called dynamically linked library, DLL. And this is the common approach to link library now, or link, yeah, usually it's library because you don't usually do DLL for your own programs. Okay, so only the libraries that you use that will be linked dynamically. Okay, so it's common for modern operating system, and here is why. Okay. So since everything is linked, not everything, but the libraries are linked during the runtime. What does that mean in terms of space, the size of your program? I mean, in terms of the executable. Since the programs do not contain the library, which means that it has less number of lines, right, in your executable. So it should be smaller, right? So because the program is smaller, it takes less time to transfer the file, right? If you want to send the file through email, it's easier now because it's smaller, okay? And also it takes less memory to run the program because again, remember when we talk about memory, right? But memory allocation. When we run a program, the whole program is copied into the memory, right? Into the stack and into the static, right? The code part will be in your static memory. So now, if I run a program without the library, then it will use less space in the static memory, right? So now if I run more programs, it will use less memory because they share the library, right? So I don't have to have that multiple copy of the library in the memory, okay? But of course, because you have to do the linking during runtime, you are using a little bit of your CPU time to deal with this linker, okay? So, and there's also another possibility that somehow your operating system cannot find the library, then you'll be in trouble, right? So a lot of times, for example, if you try to run a program and your library is not updated, okay, then Windows will usually pop up a message saying that certain .dll cannot be found. It's because maybe your driver is not updated, so that it cannot find that particular library from that driver. So you may want to go to that website, the driver's website, to get an update so that you can run the program again. Okay? So this is the drawback. But what about upgrading a library, updating a library? Since the library is not part of your executable anymore, right? So now if I update the library, it doesn't affect our original program, which means that I don't have to recompile the program. And that's why Windows and modern operating systems do that, because it doesn't make sense to ask the user every time there's an update in the library to have the user recompile the source code, because the user don't really have the source code, because this is a company secret, right? You don't want to share the source code to the customer. So now all I need to do is just to replace the library file, and now the linker will get the updated version during the linking and during the runtime. Okay, but of course the overhead is bigger. Okay, and also if the program does not have this library, then you cannot run the program. So now having the executable is not enough anymore. You have to make sure that the target computer also has the library files in order to run the program. Okay, so this is dynamic linking. And even though the overhead is more complex, but actually it's reduced the complexity of running the program actually, because it removes a lot of hardware issues, right? For example, the bottleneck of size, right? And have inconsistent version of the library, these kind of things, right? So overall, the benefit is more than the disadvantage of the dynamically linked library. So, and that's why modern operating system use this scheme. Okay, so how does it work? So during the runtime, basically, the operating system combine these libraries with the source code in the machine code level. So if you take operating system class, most likely you will learn how this works. So just stay tuned when you take the CSE 150 in the future semesters. Okay? But again, if you want to take CSE 150, make sure you take CSE 140 first, because in order to understand how operating system works, it's better to learn how the CPU works first, because operating systems are based on CPU. So even though in our school, we didn't really have a prerequisite of 140 for your operating system class, but I highly recommend you to take 140 before 150. Okay, you can take it together, or take them together, but it's a lot harder. Okay, so that's linker. If you have any questions, email me or come to my office hour. I'll explain it again. Okay? So basically, it's just to combine all the object files as well as the library file into one executable. Okay? So that's called statically linked. And there's another way to do it. Modern way to do it is called dynamically linked library, which is done during the runtime. So it's not part of your loader or your memory. It's your operating system job to do that. Okay. So now you have the final executable, and that's pretty much the end of your GCC job. Okay. So once you have that, GCC will save this file into your hard drive, and that's it. Until you type / and then your program a.out. Now the loader kicks in. So what does the loader do? Basically, it just execute your executable job, executable code, and the output is just the execution of your program or running your program. Okay? So technically, it doesn't really translate anything or convert your code. All it does is to load your code into the memory. That's all. Right? Because after you compile, your code or your program is stored in your hard drive. And only when you try to run the program, the loader will copy that program and into your memory and prepare everything for your CPU to run. And this is actually part of the job of your OS. So again, you will learn more about the detail in operating system class, okay, in CSE 150. Okay, so what does it do actually in detail? So it will read the executable file, especially a header file, to know how big your file is, because everything will be copied into your memory, right? And it will go to the memory to find out where in the memory so that it has enough storage to store your code and data, right? And this is the static part of your program. Okay? So copy the tags and copy the global variables inside, okay? And then prepare the stack memory too, because what is the first function a program will run? Main, right? So when you run a program, always start from a function. which is the main. So since main is a function, you need a stack memory. So this is also where the stack is prepared. So you will copy the argument that you pass into the program, into the main, into the stack memory, and then initialize your machine registers, right? Because you're going to have a lot of registers to be used, right? So you clear those registers, okay? Because you're running a program from scratch, right? And then have your stack pointer pointing to the first stack, because that's where you're going to run the first program, right? And then jump to the startup routine to copy all the information you need into the registers, and then set your PC to the first line of code. PC again is the address of your instruction, right? So you're starting from the first line of your main, and then from there it continues from the CPU now. Okay, so you initiate the execution, and then now it's the CPU job to read one line at a time to execute it, and we're going to learn that pretty soon, okay, after a week. Okay, so I'm going to end part 1 of lecture 16 here, and then in part 2 we're going to use this C example to run through the whole process of converting C into assembly language, into object code, and then finally we have the executable.